Hello, everybody. Okay, so here's a problem from our assignment where the topic is the chain rule. And I think this is a good problem to do at this point in the class because it involves several other things happening together. There's some algebra that we might need to talk about. There's some other rules besides the chain rule. And so I think it's a good question to do. But here it is. I'm given this function y equals 2x squared plus 5 to the power negative 3, and I want the second derivative. That's what, in Leibniz notation, that's what this means. And I don't know, at least me, I don't know of any way to get to the second derivative without finding the first derivative first, okay? So the process might go like this. I'll find the first derivative, and then I'll find the derivative of that with whatever rules are applicable, okay? So here goes. Here's my function y, all right. And I notice that that is a composition of functions. Okay, we'd use the chain rule for that. Here's the chain rule for a composition, f of g of x. Derivative being f prime g times g prime x. Okay, f prime of g of x times g prime x. And maybe so you can see that this is a composition. I mean, I am assuming a little bit there that you've learned some algebra and you've seen composition functions before there. That's where people normally learn it. But here's how it's a composition. If I let f of x be x to the minus 3 and g of x be 2x squared plus 5, and if I put g inside of f, it would look like this, and that's what we have. Okay, so that's how I'm seeing it as a composition. And to help here, I wrote G in pencil and F in my red pen, just so you can see that both functions are there like that, one inside of the other. Okay. All right. So that's what we have. So my derivative would be, okay, I would have to find the derivative of like x to the minus 3 power. To do that, I'd bring the negative 3 down in front, subtract 1 from the power. But I'm supposed to have g still inside of that. So 2x squared plus 5, negative 4 power, negative 3 there. And then this part, that's the derivative of g, or in our case, the derivative of 2x squared plus 5, which is 4x. Okay. And I could collect my terms together there. And I say, well, I got 4 and negative 3x, that's negative 12x. And I could put that negative 4 exponent down below the bar and it will become a positive 4. So I'll write it like that and I'll say, okay, here's your first derivative. Okay, now the objective here was to find the second derivative. Well, why might we do that real quick? Well, in a recent lesson that we had, we talked about if I have a function that measures the position, the location of a moving object, the first derivative will be its velocity, and the second derivative will be the acceleration. Okay, all of which are important when we're trying to analyze motion. In any case, I find the second derivative as the derivative of this. Okay, now in order to do that, I see I'd have to use the chain and quotient rules together, because this is a quotient on its own, so the quotient rule is applicable. But when we use the quotient rule, we'll have to find the derivative of this function on the bottom as part of that process. And that is a composition. It's kind of like where we started, like finding the derivative of 2x squared plus 5 to the 4th power all on its own is a lot like finding the derivative of 2x squared to the 5th power, 2x squared plus 5 to the minus 3 power. It's a lot like that where we started to find the derivative of this. Okay. Now I thought, why don't we just get some of this out of the way? Like, if I use the quotient rule to find the derivative of this, then I'm going to need to know the derivative of just that bottom function, which will require the chain rule. So I thought, why not just do that and get it out of the way so we have it when we need it? So if, when we use the quotient rule, we need to find the derivative of 2x squared plus 5 to the 4th power, here's what it'd be. 4, 2x squared plus 5, 3rd power times 4x, or 16x, 2x squared plus 5, 3rd power. Okay, now for the quotient rule. I could summarize the quotient rule like this. It is the derivative of the top function, I wrote top prime there, times the bottom function as it is, minus the derivative of the bottom function, I wrote bottom prime right there, times the top function. Okay, over the bottom function squared. So there's my work for that. And you notice when I said, what's the derivative of the top function? Well, the top function is negative 12x. The derivative of that on its own is negative 12. And the derivative of the bottom function, well, I worked that out ahead of time with the chain rule. This is the chain rule right there for the derivative of 2x squared plus 5 to the fourth power. 16x times 2x squared plus 5 to the third power. So there it all is. Now, there's the calculus extent of this problem. Now, I think at this point in our class, there's a lot of algebra. Like, you know, maybe the first 1 or 2 steps is calculus, and then there might be several steps after that, just trying to get that answer reduced as much as we can. Because, you know, that the calculus answer, the answer you get from the chain rule, let's say, it might be overly complicated, more complicated than it needs to be. So time for some simplifying. What's easy to do here? I guess the most obvious thing is I got a negative 16x, which I can multiply by negative 12x. So I'll get positive 192x squared. Okay. From there, I can do some factoring. Like I notice here's a term, 12 times 2x squared plus 5 fourth power. And then here's another term, 192x squared, 2x squared plus 5 third power. These two terms have a common factor. That common factor is a negative 12, which divides both 12 and 192. Okay. And there is also in common 2x squared plus 5 to the third power. So I'm factoring that out. I'm factoring out a negative 12 and a 2x squared plus 5 to the third power. What's left over when I take that away is, well, so I got a 4 here. What if I take a 3 away? I'm left with 1, 2x squared plus 5 to the first power. And then about this one, what's left? Say I take away 12 and 2x squared plus 5 to the third power. What's left? Just a 16 negative and an x squared. Okay, so I factored out. This is what's left from that if I factor this out. Okay. What else can we do? When I'm looking at this, I notice a few things. I can combine some like terms, 2x squared and negative 16x squared. That'll give me negative 14x squared. But also, I see that I'm dividing like things here. I got a 2x squared plus 5 third power over 2x squared plus 5 to the 8th power. So that can be canceled or reduced. Like the laws of exponents allow us to do that. If these are the same, then I've got the same thing to the third and the 8th power. It's going to be 1 over 2x squared plus 5 to the 5th power. By analogy, it's like this. If I had 2 to the 3rd power over 2 to the 8th power, if I cancel 3 of these 2's, I'm going to be left with 5 down there. So all that amounts to when reduced is 1 over 2 to the 5th or 1 over 32. You can check the math there and verify that the numbers are right. By extension, I'm doing the same thing here. Okay. All right, so I cancel that out. I'm seeing a 5th power down there now, and I think you could leave it like this. You see that right there? You could leave it that way. At least I don't have a problem with that. I noticed the answer on my math lab, though, has the negative distributed back in there. So, we can do that. So I take this negative 1, and I leave the 12 behind, and I distribute the negative 1 in there. I'm going to get positive 14x squared and negative 5. And then there's the answer that you see in the question on my math lab. Okay, now as some notes, I mentioned the algebra for canceling the exponents with the 3rd and 8th power. But also, there are options in which rules you can use. Like, I happen to use the quotient rule to find the derivative of this, okay? But you don't have to do that. So I'll say, like, could we have left dy over dx, the first derivative, not as a fraction? Meaning, like, put the 3 and the 4 together to get negative 12x, but then just leave this 2x squared plus 5 to the negative 4th power. Could you have left it like that and worked it some way? And the answer is yes, you can. What you would do is use the chain and product rules together, because now I have a product of functions rather than a quotient. So you can still do it that way. I don't think it would be easier to do it that way. So I showed you like this, all right? But, you know, if your instinct tells you to use the product rule, it will still work. You might even try it right now and see that you can come to my same conclusion right here. Okay, so I think that would be a good exercise, because even though I might think to do this with the quotient rule, and I think it's easier to do it that way, whether something's easier or harder is just a matter of opinion. So you might try something different and see how it works for you.